That's it? It's so quick. It's like, where's the waiting for YouTube to pick up the stream, waiting to make sure that it's actually working? Yeah. All right. Fine. Here we are. We did it. Yeah, I know. I saw that. You know what? So someone was mentioning that I haven't been saying people's names, so I'm going to say a bunch of hellos. Because hello to Fifth Dimension, Bob Muller, Cool, Ian Farquaad, Jim Beardsley, Johnny J, Johnny Zed, Larry Beckham, Larry King, Popcorn Power. I guess people don't even know to say hello anymore. So say hello now. Necroticus, Ian Farquaad, Corey S, Trey Harmon. Hello, Trey. I'm saying your name. Oh, the good old days. Larry King. All right.
Larry King.
Yeah, Larry King.
Wow. That's a good get.
David Dunn. Fifth Dimension. I think I already said your name. There we go. All right. How's everyone doing?
Doing all right, Fraser. How are you, man?
Good. We said nice things about you on an interview that I did a couple of days ago. I was talking to Dr. Joanna Barstow. She is an exoplanet atmosphere researcher on the aerial team.
Yeah.
And she wasn't aware of the exciting new Exomoon candidate that you guys had turned up. And so we were talking about exoplanet atmospheres and wanting to talk about what are the implications for Exomoon's atmospheres and can we do observations of those? And she was like, I hadn't heard about this. So hopefully she'll be digging into that.
Really?
Yeah, atmospheres is a thing that maybe we can talk about whenever we get to it. But yeah, Exomoon atmosphere is not crazy far-fetched to be thinking about doing that sort of stuff at some point.
Yeah. I think it's a pretty exciting field. So do we look a little blurry to people on the screen?
Actually, to me,
I know we do to us on the screen that we have. I'm just looking at the one that's being put out to YouTube, and usually, like when we're doing a show with Pamela, she looks crisp and clear, and the rest of us look a little bit blurry. And I wonder, Pamela, because I know you're listening, always listening.
They can hear me too.
Oh, they can hear you too. Okay, great.
Yep.
Are you like taking a small window somewhere and then scaling it up?
No.
To make the view?
No. Let me check what my output resolution is, because you guys look crisp and shiny on my monitor.
Yeah.
Like super crisp and shiny.
Do we? Okay. All right. I mean,
So I'm outputting at 720.
oh, do it.
Okay. Do you want me to restart the stream at a higher?
No,
Okay.
no, absolutely
Okay.
not.
Wow. Okay. So
Yeah.
next time I will go out
Next
at.
time.
So what do you want me going out at?
I would go at HD, like go at
1920 by 1080.
by 1080. Yeah.
Okay. Yeah. No, I was
Yeah.
sending you out at 720. That's what was happening.
Yeah. So I mean, garbage in, garbage out. So however you're scaling it, there you go. Correas is saying that Chris looks sharp, Fraser a little less, Alex and Carolyn less than that. Actually, Chris's
Yeah.
lighting is really good. You got it
Yeah.
nailed, Chris.
You guys are always complimenting Chris's lighting.
Yeah.
So
I
so
love
you
it.
may want to clean your camera off though, because you are a little foggy.
Oh, well, there you go.
Yeah, I don't know. I'm using a Mac built-in camera, and
Yeah.
usually surprisingly poor resolution on those. I think. I mean, this
Yeah.
machine's a few years old.
Yeah, and Carolyn's network likes to compress her.
Yeah. And of course, I'm using Starlink, so
You look fabulous on
Show
my
off.
screen.
Show
Wait.
off.
I'm going to
We're still
take a
waiting.
photo.
You're using Starlink, Fraser?
Mm-hmm.
Part of the problem, then.
I know. Yeah, I'm a walking, talking hypocrite. Wait till I give Starlink a hard time later on. I can do both things.
Yeah.
How else could I instruct people about the dangers of Starlink
Yes,
without
indeed.
using Starlink? There's no other way to communicate the dangers of Starlink.
Such
Well, I've had that
chaos.
thought too, and we're on the waiting list for Starlink here. So
Yeah, it's stretched out pretty
There you
far.
go.
I'm really glad we were able to get it
Yeah.
as quickly as we did. All right, let's start. I'm rabbit holing. Okay. Hello and welcome to the Weekly Space Hangout for Wednesday, January 19th, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about an Exomoon candidate. More information about the local bubble, what space does to your blood, and the last time the Milky Way ate a galaxy. Joining me this week, we've got Dr. Alex Tichy. Alex,
Hello, Fraser. Good to
how's
be
everything
back.
going in Taiwan?
Things are good, man. I love it here.
This is a pretty exciting episode. I mean, your news is also your work, is also
Yeah.
your research. This is a little bit of the snake eating its own tail, but we're going to dig deep into
Hey,
this
we couldn't
incredible
miss this.
discovery.
We couldn't miss this news item.
Yeah, no, for sure. I'm glad
gotta be allowed to
you
talk
happen to
about
be
it.
showing up this week.
Yeah.
We've got Carolyn Collins-Peterson. Hey, Carolyn.
hey, how are you?
Good. So have you been watching the bit by bit changes to the James Webb Mirror? Have you seen that you can actually watch
Yeah.
the progress of
Mhm.
the different mirrors
Yeah.
as they're aligning themselves?
Well, I followed that, and I also tried to train my EV scope on it to watch it as it's moving to L2.
Were you able to capture it?
I sort of, but it wasn't the greatest.
Yeah.
Yeah.
You've got an EV scope as well. You and Dave.
Yeah.
Yeah.
And as soon as I got it, it started to snow, and we had crappy weather for the last
Right.
2 weeks.
Well, obviously that's your fault. You summoned snow
Yeah,
for the
yeah.
whole surrounding. Yeah.
I didn't
So are they
buy
pub-
the extra can of cloud begun. So
Right. Yeah.
Are they?
And,
They
of course-
must be publishing where JWST is in the sky, right? Like they've got like real.
yeah,
time
there's an
estimate.
ephemeris you can download. Yeah.
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 Yeah, and I think it's like magnitude 15 now. Like I think that's
It's
it.
pretty big.
Maybe 17 is going to be its final L2,
Mhm.
sort of when it's finally loitering at L2. But I guess just look
Yeah.
toward L2. Everybody knows where L2 is.
Yeah. Well, and there's some diehards that are going to keep trying to follow it all the way. So
Yeah,
right now we have clouds and it's about 10 degrees out. So I'm not going to be doing it tonight.
right. And of course, we've got Chris Carr. Hey, Chris.
Hello, feeling good. Actually, I didn't announce this, but I actually submitted my first paper last week to
Congratulations.
monthly notices, and so finally
Is
an
it-
author.
Is it on archive or is it as well?
Yes, it's on archive.
Okay. And what is the title?
Migration and mixing in the galactic disks from close encounters between Sagittarius and the Milky Way.
So this sounds kind of similar to the story you're going to be talking about today, just a different dwarf galaxy.
Yeah, it's all the same galaxy, so yeah.
Well, at least Milky Way is definitely a common element in this.
Yeah.
All right, let's move on to this week's news. Actually, you know what? Before we do that, it's so weird. We don't have a guest this week, and so I'm out of sorts. But let's talk about our good friends of the Weekly Space Hangout crew. They're friends, our fans.
Mhm.
They are the executive producers of this show. They are an incredible community that keep us organized. And if you want to be a part of this community, go to wshcrew.space. You can join up, and they will make you an executive producer, and then you can bring on guests. You could have coordinated the guests we don't have this week, so could have been you. All right, let's get on with the news. So, Alex, you discovered an exomoon.
Yeah, possibly, right? Oh, so we always have to preface these things. When it comes to, with the new planets, people say we discovered this, we discovered that. When it comes to exomoons, it's still such a fresh field, and there are always these sort of lingering uncertainties. And so we come out, and the best thing we can do right now is say, looks like an exomoon candidate. And, what that means is we've turned over every rock that we can think of to try to rule it out. And so this new paper for this system, Kepler 1708b, and it gets a Roman numeral 1 after it for the lowercase Roman numeral 1 for the exomoon candidate. David Kipping is the lead author here, and he's done a fabulous job looking at all of these cold planets, 70 cold planets and all. So if you think about the solar system, the vast majority of the moons that we have here are out at the colder end of the solar system. Jupiter, Saturn, Uranus, much farther from the sun is where we find most of the moons. And so it's a good bet that maybe when we find moons in other planetary systems, they're going to be around colder planets as well. Right.
So hold on a second. So talk about this. So they looked at 70 cold planets.
Yeah.
And how did they look at them, try and tease out if any of them have an exomoon?
So it's all going through the Kepler data in this point. So Kepler, is now been retired for several years, but this data still yields new discoveries, which is really amazing. So going through all of these planets and fitting them and seeing if a moon model is a better fit to the data. And then, there's all sorts of sort of sanity checks. What could the telescope be doing, or what other sort of astrophysical explanations might be fooling you to infer that there is a moon there? Maybe there's sunspots or something that are mimicking the look of a moon. So he goes through like I say, 70 planets and emerges with this one. There's really 3 that they look very, very closely at. And then of these, one of them emerges where we say, can't rule out a moon based on all of these other sort of tests that you might try. Looking at maybe the telescope is doing something, maybe the star is doing something strange. And then you get the data, and the moon is the best explanation to almost 5 sigma. And so in a lot of fields, you'd say, all right, slam dunk, we got it. But we're looking at this, the data here. We've got 2 transits. Now that is to be expected for a very long period planet, because the planet's so far away, it takes a long time to orbit, and so you only get 2 transits in the Kepler data. That's as little as you could possibly work with, right? And one thing that anybody who's been following the exomoon search might know is that these transit timing variations tend to be quite central to the search, right? This is the idea that the moon is pulling on the planet gravitationally, and so it makes the planet wobble. And so that means that the transits, sometimes they're early, sometimes they're late, etc. The problem, though, is that if you have 2 transits, there's no way that you can measure a variation in the orbital period, or you can't measure a wobble. You can draw a line between 2 points, 2 data points, and then you need that third to see whether or not it's not strictly in a line, but if there's variations here. So we don't get TTVs with this particular system, but naturally that's something that we really want. So we're going to definitely want the more transit observations of this planet.
So if it does exist, what are its characteristics?
So this is another quite interesting finding here. The moon is larger than the Earth, substantially larger than the Earth. You call it a super Earth, or more likely a mini Neptune, having sort of a gaseous envelope. Now, again, this is maybe the second big exomoon candidate that we've had in the last several years. The first one was Kepler 1625b, and that moon, also the moon solution, suggested again a very large moon, and so that has been reason enough for a lot of people to be skeptical that it's a real thing. It's so different than anything that we see in our solar system, and so people naturally say, well, can that even be a real thing? I mean, how do you make such a thing? Turns out you can, but it's definitely a sort of a weird thing. Now we've got another one of these sort of large moons. People were calling it a super moon, and that's going to get confusing. But it's another very large moon, and so Jesse Christensen, who was one of the co-authors on the paper, I saw her saying on Twitter, the fact that we found another one of these very large moons kind of lends credence to both of them now. But, now it's not a weird thing. Now you've maybe found two of these things. Again, uncertain. At least we know from a theoretical perspective that you can form something like this. And naturally, they're the lowest hanging fruit. They're the largest things that you could possibly see. And so to some extent, you'd say, well, that is the first thing that you should see. If you're going to see anything, you should see the really big ones first.
They're the hot Jupiters of exomoons.
Exactly right.
Yeah. So, I mean, obviously Kepler is not going to be able to help you because Kepler is dead.
Right.
You got Cheops. What are some ground-based observatories? James Webb, what can you do to try and do further confirmations of this system? Right.
So, if memory serves, I think I might be wrong about this, but I think Cheops and Kepler don't even overlap. I think Cheops can't look at the Kepler field or something. I might be wrong about that, but I looked into it one time. What can we do with Cheops? And we're like, well, we can't even do anything of a sort of a follow-up. I might be wrong about that.
Okay.
But there's TESS, obviously. If you get so lucky that TESS is looking at the Kepler field at just the right time. But this is, this planet orbits, I think the next transit is in 2023. And so TESS would just have to be looking at Kepler field at that time. And the chances of that are somewhat low. I haven't looked into whether or not it's going to happen, but I would guess maybe not, probably not. So that leaves you ground-based and JWST. And ground-based would be great for potentially looking for these transit timing variations, right? So Paul Dalba is a scientist in UC Riverside, I think, recently led this citizen science project with observing a transit of Kepler 167e. This was really cool. They used the EVRYScope community, or EVScope. Yeah, you guys know the one I'm talking about. This telescope that everybody is so into right now. They got people all around the world to collaborate to jointly observe this transit because it's a very long period transit and the Earth is turning. So everybody on the ground can just get one little piece of the transit. But if you observe it globally, then you can really see the whole thing. So I would love to see something like that leveraged for this planet as well, so that we could again observe the entire transit. And then JWST clearly is going to be phenomenal. If they will award that time, I think it's something that we'll certainly be putting in a proposal to try to see it with JWST.
So if it does exist, again, give us a sense of what kind of interaction you would have between the planet and the moon. How would it be different than just a Neptune flying around?
Well, interactions. I mean, I've never really thought about it too much. When you have a planet and a moon, they are tugging on each other. They're inducing tides, of course. We think of Io, for example, is got all kinds of volcanism on the surface because it's so tied in with Jupiter. This planet is the moon is about 12 Jupiter radii, so it's quite a bit closer in than, say, the Kepler 1625b moon, again, if it's real. So, there could be some tides there. I haven't really
would it be tidally locked?
Implications of what the moon might be doing to the planet, or the planet might be doing to the moon. In this case, the mass ratio is still probably, I think we're we're closer. My estimate is that we're closer to the Earth and Moon mass ratio than we are something more like a Pluto and Charon type of situation. Yeah.
Interesting.
Wait, Alex.
Yeah.
So how developed is like the theoretical modeling of like exomoon formation, and are moons of this size and also moons potentially having atmospheres? Is this like a fairly common phenomenon that you would expect theoretically, or is it obscure?
Well, I don't think it's hard to say commonality, right? As an observer, I want to see them and then estimate how common these sorts of things are. When it comes to moon formation more generally, I think very naturally it has up until now been predicated on explaining what we see in the solar system, right? And there's a variety of different ways that you can get the moons. But people have clearly, understandably written, how do you get Jupiter's moons? How do you get Saturn's moons? How does Pluto get its moons, et cetera, et cetera? Because we haven't had any sort of observational frame of reference for exoplanetary systems, right? And exoplanets similarly have sort of changed our thinking about planetary formation as we've discovered those things. So similarly, these giant moons have got people scratching their heads, but there have been a few papers since, particularly 1625, and I'm sure we'll follow on from this new work as well, to say, can you get something like that? So that's the first question. Can you even make it? And, there have been several papers that say, yes, you really can. And it would probably be something like a capture scenario. So that originally this was, a separate object, and then it kind of gets pulled down into orbit around the primary. That seems to be, rather than a formation in a disk, more like the moons of Jupiter or Saturn, which is almost like analogous to a planetary system forming out of a disk. It seems unlikely that you would get something this large out of something like that. And so, it's a little more plausible, I think, that you had something free-floating Neptune that gets pulled into orbit.
So when I interviewed you a couple of months ago,
right?
Did you know about this?
I knew it was in the pike. Yeah. Coming down the pike. It's been a long time coming, actually. Yeah. Yeah.
Well played.
I think maybe I teased it at some point, or I said,
I don't think
we got something.
I don't think
something coming.
You indicated that you had a pretty solid candidate that you guys were going to be announcing in a couple of months. I do not believe that was our conversation, because then I would have just needled you until you gave up the goods. So I guarantee that you didn't tell me. Still, incredible work, fantastic. It's great to hear right from the horse's mouth in this case. Congratulations, and I look forward to many more of these exomoons. Sounds great.
Right.
All right, Carolyn, let's talk about the local bubble.
All right, we'll talk about the local bubble. So last week, of course, we had the press conferences from the canceled AAS meeting.
Right.
I guess you guys probably talked about that. And a lot of news came out last week. So one of the stories that kind of caught my eye was about this bubble. And I'm going to back out a little bit before I talk about the bubble and talk about something called the local interstellar cloud, which we're in the middle of, and so is the bubble. So the LIC, as you can see here, it's an overdensity of hydrogen. The solar system has been going through this thing for several tens of thousands of years, and we're going to exit it fairly soon, maybe within 1,000 years. And the big questions have always been, what's it going to be like once we get outside of this sort of protective cloud of stuff? We're going to have more cosmic ray bombardment or radiation or whatever. And we didn't really know a lot about it until the 90s. I mean, people knew that it was there, but I worked with Flinsky at the University of Colorado for a while back then. He used the Goddard High Resolution Spectrograph on HST to kind of probe through this local interstellar cloud. He looked at 16 or 17 stars and did some spectra of what was going on through the cloud, what's there, what the abundances are, what the motions are of the cloud, and basically map the extent of the local interstellar cloud. So as you can see, it's this big cloud. It's about 10 to 20 light years across in each direction. And you see the sun in the middle of it. Well, around the sun, if you want to zero in on it, then we have this other little structure called the local bubble. And it's sort of this cavern, smaller than the LIC. It's only about 1,000 light years across. And it's like a cavern that's been blown out. You think of it like a cave or something that's been blown out. And so the question was, well, there are a lot of questions. One of them is, why is the sun in the middle of this? Is that coincidental or not? But this cavernous bubble of stuff is basically extending out about 1,000 light years. And astronomers use the Gaia spacecraft to start charting the stars in the local neighborhood and give a 3D view of all this. And they noticed that there were several really active star formation regions at about the same distances in different directions. You can see in the image here. And so this is basically where the outer shell of the bubble that we're in is expanding out into the interstellar medium, and it's causing new rounds of star birth. So the big question was, what causes this bubble? Why are we seeing this happen? Why are we in the middle of it? And the current idea is that there were actions of star birth and star death about 14 million more years ago. These hot young stars were formed. They had short lives. They died as supernovae. And in the course of all of this action, these stellar winds and all the activity involved with star birth basically blew this bubble. So I was kind of thinking of it like some of these nebulae that you see in the Large Magellanic Cloud, for example, where you see these star birth regions and there are these sculpted areas out. And that's kind of what's happened here. But here we are with the sun in the middle of it. Are we traveling through it? How quickly is the bubble moving? Are we going to come out of it? And one of the questions that came to my mind, and I don't have an answer for this, is have we studied the abundances of elements in the middle of this bubble to understand more of its structure? So that was really kind of left open in the story that I read about.
Mm-hmm. And so the idea is that at some point over the last few million years, multiple supernovae have gone off in our area, contributing to this bubble and contributing to these clusters of star formation that's happening all around us.
Right. And then you look at and in the image that they kind of published with it, you see these areas of star birth. And so in a few million years, those largest stars, however long it's going to take those largest stars to start popping off, they will, again, start popping off a supernovae and form new bubbles. Kind of the big story here too is that this expanding shell is expanding into the interstellar medium areas where there's higher densities. We're starting to see these star birth regions really start to wind up and start creating more stars.
So is the expanding bubble, this overdensity bubble, causing the star formation and leading to the supernovae, or are the supernovae causing the bubble to expand outward?
Well, there's two sets of them. So there were the stars from millions of years ago that formed and exploded, and their stellar winds and their activity forced this bubble to start expanding. And now it's expanding the interstellar medium and forcing new sets of star formation, which eventually some of those stars will start dying as supernovae. So it's kind of a recursive process.
Yeah, it feels kind of like dominoes falling. Like you've got this chain reaction that's going off across the Milky Way as supernovae are detonating. They're collapsing star clouds of gas and dust. They're turning into stars. They're generating hot stars. They're detonating supernovae, and maybe this local bubble is just an example of this washing past dust. Yeah.
Well, one of the things that came out at the end of the story and in the discussion was astronomers have been trying to. I mean, this isn't a new idea, obviously, that this is happening in the galaxy, but you needed to have examples of it, and you need to start studying the stellar populations around the sun, which are the easiest to study. And then you see these areas where these overdensities are being pushed into creating starburst formation, essentially. And so now we have this evidence, which we didn't have a lot of before. So now I guess you start looking at other places farther away to do that. The other thing that this kind of said to me is, we kind of grow up thinking, oh, it's the empty wilds of space. There's nothing out there. Well, there's a lot out there, and there's stuff happening out there with starbirth, star death. There's recursive action of it. Then basically it starts new rounds of starbirth by this compression action that's happening.
Chris, how would this kind of look over time? Like if we were early on in the history of the Milky Way, say, just when the star formation was at the highest point, would it be the same kind of activity, or would it be just a lot busier? And will there be some point in the future when maybe the supernovae can't connect and can't collapse star clouds and they stop?
Right. So I've been trying to wrap my head around this image, and I think what's like what's going on here, and it kind of references in the piece is like if you had like this supernova that went off around 14 million years ago or so, and it sort of launches this expanding shell of material, then like as that expanding shell interacts with the ISM, it like as it's sweeping up material, it eventually in the most overdense regions, cooling is more efficient, and so which results in this like accumulation in these small areas, which lead to the star formation. And I've been trying to like sort of reconcile that picture with this idea that because when we typically think about star formation, like supernova, it's usually as a way to suppress star formation, because it's a way of sort of removing removing gas like out of the vicinity, either in these winds, which are able to lift the gas out of the galaxy, which serves to reduce star formation overall because you're removing the fuel. And so at least in my mind, I've been trying to really understand how it seems supernova can both suppress star formation, but also, as this picture seems to be illustrating, could also activate it as well. And this does connect to our broader stories of like how galaxies evolve and how that star formation affects the distribution of baryons throughout the galaxy. So I'm actually quite intrigued by this, and I'd be interested in learning more about it.
I think it was widely considered the biggest story last week, the biggest story coming out of LAS. The precision of their measurements using Gaia to measure all of these star clusters around, and was quite well received, and it's a pretty exciting announcement. I just sort of like, I imagine in the past when the clouds were denser. So I guess that's the question: are supernovae quenching these, or are they causing regions to collapse? And I understand that that's still well, but I understand it's actually still a bit of a controversy, like what Chris is saying. Like it's kind of, in some cases it starves them of fuel because it blows away the clouds, but in other cases it may cause local overdensities that causes a cold gas cloud to actually gives it the trigger to actually collapse.
Yeah, and I think this is actually like a very.
I think too, if it's situational, then we have to ask, what are the characteristics that make it one situation that you can have this star formation happening versus the quenching in another situation? What's different about those two? And that was sort of the question that I didn't really get answered in the Q&A.
Yeah. Very cool. All right. Chris,
I do have one other question for Chris. And that is, would we see anything like this in the you were asking about it in the very early galaxy formation, when you have some of these newer, or some of these clusters coming in that, or galaxies that have stars that are essentially dying, as they're coming in, as part of these dwarf galaxies, their abundances of their elements and that sort of thing is not going to be reflected in the very individual areas where those supernovae happen as those stars die.
Yeah. So the abundance question.
See that sort of starbirth.
So like when you mention abundances and like trying to sort of record more detailed measurements of the chemistry of these starbursts, like my mind went to, if you were able to get these measurements of their abundances, would you be able to reconstruct the chemistries of the supernova that went off, that ignited those formations, like using the chemistry, using the chemistry of the new stars in order to get to the chemistry of the progenitor supernova.
Really interesting.
That's a little outside of this, but I was just thinking, if you have these successive eras of star formation and star death, that's going to be sort of this going to leave a fossil record throughout the galaxy.
If only there was a really powerful telescope that could try to scan some of this information. All right, Chris, tell us about the Milky Way's most recent meal.
Yeah, sure. So I guess one of the hallmarks of how galaxies are formed within our current framework of cosmology is that the accumulation of smaller galaxies like dwarfs through mergers and accretion events gradually build up larger and more massive galaxies like our Milky Way. And we see this firsthand when sort of tracking galaxy formation in cosmological simulations. And we also see this directly in observations of the high redshift universe, where these sorts of direct disruptive collisions between galaxies were quite common during that time period. And since our home galaxy, the Milky Way, is no stranger to this process, studying the Milky Way offers us a chance to examine the assembly process of galaxies clear and up close. An arena where the debris and remnants of this assembly process are most apparent are in the Milky Way's stellar halo. So these are stars that aren't necessarily associated with the disk, but still bound within the galaxy and the halo at large. And it's here where you'll find the remains of disrupted dwarf galaxies, stellar streams, and stripped material from neighboring satellites like Sagittarius, which was the subject of a recent paper, which if you're interested.
Are you talking about the famous migration and mixing in the galactic disk from encounters between Sagittarius and the Milky Way?
Oh yeah, many people are talking about it. You should.
yeah. It's a page turner. Yeah.
Yeah, so like interactions with Sagittarius and the Magellanic Clouds, which will be feasted upon in the future. But this new study attempts to use observations of the Milky Way stellar halo from the H3 survey in order to reconstruct the Milky Way's last major merger 8 to 10 billion years ago. That goes by the name the Gaia sausage Enceladus. So the term sausage, as I'm sure we've gone over several times here before,
Let's do it again.
Refers to the sausage-like shape stars in the stellar halo make when you plot their circular velocity versus their radial velocity. I think I have a plot of it on the next slide.
The worst name for a galaxy.
Yeah,
how can you name a whole galaxy?
I can't bring myself to mention it.
An outrage.
The sausage.
And Enceladus, like we've already got something named Enceladus.
Yeah. I think you need to go back to the drawing board on this one.
Well,
I can workshop it right here, actually.
well, I didn't choose.
That looks like a fried egg to me. That plot. Why don't we call it the fried egg galaxy?
The jellyfish. No, there's already a jellyfish.
Yeah.
Well, I didn't choose the name, so don't blame me. So when you plot in this space of like circular velocity versus radial velocity, stars in the stellar halo, they form this elongated shape spanning a wide range in the radial velocity, but a very narrow range in circular velocity. And this just means that these are stars that are overwhelmingly on these eccentric orbits in the halo. And you can also see disk stars in this plot as well, clustered around 200 kilometers per second, which is approximately the rotational velocity of the galaxy. These stars also occupy a small range in the radial velocity, so they're mostly on circular orbits, forming like the meatball to the halo sausage. That's usually, I didn't make those up though. That's what we say in the business.
Yeah. This is how the sausage gets made. I know.
So like the presence of these stars on these like highly eccentric orbits, they also share a common age and metallicities. And so the combination of this fact was compelling evidence that these stars were deposited in a single like major merger event in the ancient Milky Way. And so like the first author of this paper, his name was Rohan Adi from Harvard CFA. And what he and his team were interested in was essentially trying to use the kinematics and positions of stars in the halo to infer the original orbital configuration between the Milky Way and the Gaia sausage Enceladus progenitor. And although we've learned quite a lot about this past merger in the past few years since Gaia, there are still many questions that remain. So like was the GSE remnant a massive satellite of the Milky Way that orbited the galaxy that was on some decaying orbit that spiraled inward until eventually colliding, or like a direct, like, head-on collision.
Mm-hmm.
These are important questions to ask because when we vary the orbital properties, like if it's a retrograde or a prograde orbit, its circularity, its inclination, changes to these properties produce significantly different distributions of debris that go on to populate the stellar halo that we're observing now, billions of years later.
And so I'm seeing in the graphic that they tracked 7 million stars in the Gaia data.
Yeah. So and this wasn't for the paper, but from the I think DR2, which allowed
Right.
them to make the discovery of the sausage.
Right. Because we're like up to like 1 billion stars, aren't we, with Gaia at this point? Plus.
Oh yeah.
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 Like a ludicrous number of stars are now being tracked. And so what was the poor galaxy? What happened?
Right. So like how they really went about this is that they conducted like a large like span, I think over 500 like simulations that sort of sampled a wide range of parameter space of like initial orbital configurations. And then sort of involving each of those simulations, like 10 billion years, you can make a direct comparison between the simulated output of the stellar halo and the stars observed in the H3 survey. And what they found is that the progenitor that is about twice the mass of the LMC hit the Milky Way on a more like direct, slightly retrograde and inclined orbit. And this configuration provided the closest match to the structure observed in the H3 survey. And a byproduct of this model, which is also quite fascinating, is about 50% of the stars now in the stellar halo, and about 20% of all the dark matter came from this encounter, from this like single event.
Wow. That's amazing. So do the stars in the halo, like if you say like a large portion of them come from this event, is that normal? Like, do you get this buzzing of stars after a like a, I don't know, you're eating, the Milky Way is making a mess as it's eating a galaxy, and then all of those additional stars eventually settle down, and then the next time when the Large Magellanic Cloud crashes into the Milky Way, then you'll see the same thing happen?
Yeah, pretty much. I like these constraints were sort of allow you to sort of better reconstruct the history of the Milky Way, and the fact that this single encounter is supplying such a large supply of stars in the halo suggests that the Milky Way has had like a fairly like quiescent history over the past like 10 billion years, and that this places strong constraints on the number of interactions the Milky Way could have had like in the past.
And this happened what, like 8 to 10 billion years ago, right?
Right, exactly. So since that time, in the last like 8 to 10 billion years, the Milky Way could not have had like another like major encounter with a LMC like object, and so this allows us to sort of look at similar galaxies in simulations or out in the real universe, and sort of allows us to ask the question of, is the Milky Way unique? Like, is this typical of like of galaxies of
It
this
seems
size?
like a surprisingly long time to not have consumed a galaxy.
Yeah, precisely. Especially if you have like a cosmology that's sort of dependent on this hierarchical accumulation to form massive galaxies. The fact that you have galaxies like the Milky Way that can last for so long without encountering another comparably sized object is kind of strange at first thought, and it's sort of an area of ongoing research whether or not this may be indicative of the Milky Way being unique, or whether it's a question, or if it's pointing to a larger question in our cosmology of how galaxies like this form.
Right. And when you think about the fact that we've got Andromeda due for collision in the next 8 billion years from now, we've got the LMC and the Small Magellanic Cloud both on the way out. It's surprising that it's
Yeah,
been so
funny enough,
long.
like a lot of fun stuff awaits the Milky Way. So
Yeah.
even though it's been quite lonely for 8 billion years, it's going to have a ton of fun in the next few billion.
Yeah, that's true. Awesome. All right, thanks, Chris.
Yep.
All right, Carolyn, let's talk about what spaceflight does to your blood.
Ooh, yeah, blood in space. I just wanted to say, I think last year I maybe covered a little bit of the second data run for Sausage Enceladus, and we still had a lot of fun with the name. So
Yeah,
it,
yeah.
it's the thing we love to hate.
I'm not gonna lie, I won't do it. I see the story and I go, I'm not gonna say it.
Not
But I guess I should.
We should have a
It's
contest.
news. Yeah.
Yeah. Well, all right. So blood in space. So I'll preface this by saying that I was interested in the story because I actually have a blood disorder that affects red blood cells. So I was reading it thinking, okay, what have they found out?
Maybe you went to
the
space.
Story that, oh, well, I wish, you know, or actually probably what's going to happen is it will prevent me from going. But anyway, space anemia is a thing, and we've known about it for a long time, along with effects on long-term travel with on the bones, on the eyes, respiratory system. And generally when astronauts come back, then all of those tend to go away, although I think there have been long-term effects on eyesight that Mark Kelly and some of these guys have talked about. And I know that John Grunsfeld has talked about it too. But essentially, when astronauts go up to space, they come back and they're deficient in red blood cells. And so the question was, why is this happening? Because it showed up even after some of the earliest long-term missions. So, and it's also kind of important because astronauts are kind of like, you know, super people, you know, they're the peak of health when they go up. So why do they get to space and then suddenly the red blood cells start getting destroyed at a rate that's about 54% higher than you would if you were here on Earth? Well, that was the question that people were trying to ask. And so a group of doctors at Ottawa Hospital and the University of Ottawa in Canada devised some tests for astronauts to take. Now, you know, they're up there on the space station and they're going to basically breathe into bags. They're going to take blood tests. All of this because these are sort of, well, blood you can, you know, measure directly, but breathing into the bag is sort of a stand-in for how much carbon dioxide you're breathing out, and there is a tracer of something that your blood gives off when it's destroying the red blood cells. So they measured 14 astronauts over a period of each one of them was up for about 6 months on the ISS. And they found this 54% overage of people destroying red blood cells in their bodies. Now, we do this all the time here on Earth. Your body just constantly recycles these things. But these guys, these men and women, are recycling 54% more. So when they're on orbit, and it starts as soon as they get onto orbit, immediately. So they basically track people for their 6 months or more that they're on there. Men and women both had the problem. Now, it's important to note that this didn't really affect their health well. They were on orbit. They're short enough missions that you don't have a long-term issue. And when they come back, they generally tend to return to normal, although it's taken some of them up to a year to get back to normal for this destruction of red blood cells. So the question that comes up is, or the implications really are, for really long-term space flight. Like we have people going to the moon and they're going to live on the moon for a long time, or Elon's trips to Mars. You know, it's many months out, many months back. Doctors want to find out what the mechanism is that triggers this overage of destruction of red blood cells, and they want to figure out if there's a way that you can stop it. Once you know the mechanism, is there a drug or is there a diet or something that you can implement that would keep people from, having this problem? So they wanted to devise intervention. So that's what they're looking for. Maybe a change in their diet. Maybe they have to change the way that they're exercising. You know, they just don't know that. So that's on the space side of it. What really intrigued me was, because I have this blood disorder, finding out that there's implications in this study for people who have anemia on Earth who are never going to go to space. If you can figure out the mechanism for why it's happening in the short term on space, could you then apply that to people who have it on Earth, figure out why they're getting anemia? Now, this is, outside of some disease that you get that causes anemia, and there are certainly plenty of those. But somebody just starts out and they start destroying more red blood cells, or they're more anemic. Why is it happening on Earth? Maybe there's a clue from why it's happening in space. And this is kind of one of those space spin-off stories that really caught my attention right away.
So I guess, I mean, do they know? I mean, or are they just tracking? They have ways of tracking it, but they don't still know what the underlying mechanism is yet.
They don't. I don't think they know. And I've actually written to the doctors. I haven't gotten an answer back yet to say, do you have a suspicion? Now, they know sort of in general how the body generates all the different particles in your blood. It comes from your marrow, and the marrow differentiates into different particles, platelets and red blood cells and so on. But and there's a mutation that happens on Earth, because that's certainly the case in my case. There's a mutation. Well, astronauts aren't going up there and mutating and then coming home and they're not mutated anymore. So there's got to be some other mechanism, and they're probably looking at that differentiation of what happens in the bone marrow.
And Popcorn Power is mentioning in the chat that radiation might be an issue, but the astronauts are protected by the magnetosphere on, say, the space station.
Well, I certainly thought about that too. I don't know what that would be, and if it is true, then wouldn't they? I mean, the question in my mind would be, if radiation were the issue, that's damage is permanent. So you're going to see that overage on Earth, and again, over the course of about a year, they return to normal.
Yeah. Yeah, but I mean, it might be different. And I wonder, though, if we have when we do have a moon base, will we see a version of it, but it's less? And if we have a Mars base, a version of it, but it's less?
Well, the question in my mind, too, is going out to Mars and you have a whole bunch of anemic people showing up. Now, there is some evidence that people just ramp up their red blood cell production in space. But a Mars mission is not just a year. It's much longer. And I know, does it sort of reverse itself when you get into the gravity of Mars? I mean, we don't know.
Yeah, absolutely fascinating. And I mean, it just shows you space is trying to kill you. Another new way.
Well, I'm sort of hoping they'll find out a way that if space is trying to kill you, maybe it'll help them find a cure, for the problem. Because if they're rapidly coming back to normal on Earth, then that does identify some mechanism, and they just maybe don't know what it is yet.
Yeah, really interesting. Very cool. All right, so I'm going to share just a quick story. Pamela didn't know about this, so there won't be a picture. But the Zwicky Transient Facility is a telescope that's based in Caltech's Palomar Observatory in San Diego, and one of the things that they're doing is they scan the sky right after sunset and just before sunrise to look for potentially dangerous asteroids, the ones that are coming at us close to the sun, the ones that we'd have very little advanced warning from. And what they found was they did a bunch they took a ton of pictures over the course of 2 years, and they got 5,301 satellite streaks going through their images. It worked out to, in the beginning at 2019, sort of before Starlink and the other satellite constellations, about 0.5% of their images were affected. But now at the sort of into 2021, they're getting as much as 20%. So 20% of the pictures that they take have a streak going through that. And of course, the thing that's added the most is Starlink. And they figure that when they reach the final constellation size of about 10,000 satellites for Starlink, you're going to get one streak in pretty much every single image. So that's a thing. The good news is it doesn't sound like it's going to be an enormous problem. Most of the time astronomers are observing, they're looking, they don't want to observe in astronomical twilight because it's a bad time to look. And you also don't want to look near the horizon, near to the sun, because it's a bad place to look. You want to look towards astronomical zenith. You want to do it at the middle of the night. And so, and at those points, all of the satellites are in the Earth's shadow. But there are these special cases like searching for dangerous asteroids, things where you do have to look during that time. And what they found is, although it is an issue and there definitely are star trails, they can remove them from their data. The issues are going to be when you're taking a picture and the killer asteroid is right there and the Starlink trail goes right through your killer asteroid and hides the data of it, and then the next night, if you're trying to plot the trajectory of an asteroid and you miss a night's worth of data. But sounds like, based on their research, it's definitely an issue, and it's going to cause a growing concern, but it's something that they should be able to, even for them, they're able to compensate for it and work around it. And I think at this point, we're seeing that the Starlinks are a magnitude 6.8, which is well below what we can see with the unaided eye. And so even in perfectly dark skies, most people aren't going to be able to see Starlinks at all. With the new sunshade that they've got on it, with the darkening paint job on the Starlinks. So I think, what we're going to find now is that the Starlinks and these other, I mean, this is just the first one, right? There's the Amazon's version. There's going to be the Chinese version. There's going to be the Russian version. Maybe Dubai is going to do one. So there's going to be more and more of these satellite constellations. There will eventually be tens of thousands, hundreds of thousands of satellites in low Earth orbit. And these are going to act as a friction on ground-based astronomical work over time as we move forward. And hopefully it won't be dire, the killer asteroid that you just weren't able to see, but a lot of it is going to be an astronomer is looking to observe some galaxy, and there happens to be a Starlink trail right through the image that they took, and they have to throw out that whole frame. And maybe they only had an hour of telescope time, and they lost 1 5-minute exposure, and now they only got 55 minutes of telescope time, so they're going to have to book more time. So that's how this is going to play out over time, is that we're going to see astronomers having to extend the amount of time that they're doing their observations for to be able to collect the same amount of data. And the more satellites that are up there, the more this is going to have to be. And telescopes are already oversubscribed already, and so you're going to see this become more and more of an issue. So there you go. He says using his Starlink to communicate this information to you.
Yeah. I actually admit it's really cool when right after launch, about 2 or 3 launches ago, we saw the whole train going right overhead.
Yeah, I've seen
that
it
was
once.
Kind of neat to watch. Yeah,
it's neat to see it a couple of times. After a while, you're like, okay, get out of my sky. But which is nice to know they do get down to magnitude 6.8. So like a lot of people are quite nervous that they're going to be filling the sky, that there's going to be this grid of satellites everywhere you look. And it's not going to be the case. They're too dim to see with your eyes. They're only visible during the summer, like the high summer at the high latitudes. But it's for astronomers, professional astronomers. They're the ones who are going to be paying the price for the existence of these. People like Alex.
Well, and it's going to complicate launch planning too. I mean, you have many, many tens of thousands of more things to dive for launching.
Oh yeah, that's a whole other. I mean, we're already seeing satellites have to make course corrections. The International Space Station, even the Starlinks, are having to make course corrections because there's other debris and other things that they're going there. And there doesn't seem to be any real global coordination between shells of where people are allowed to put their satellite trains, because that would be the solution. Is you have to stick your satellites into very specific pathways so that they have no chance of interacting with each other. And right now that doesn't exist. And so more and more collisions are inevitable. The good news is, because the Starlinks fly so low altitude, and a lot of these, they burn back up into the atmosphere within a couple of years. Once their power goes out, once they no longer have a method of propulsion, they re-enter within a very short period of time. And so, strangely, counterintuitively, the more satellites you get at these lower orbits might actually be the way to keep space safer, because the debris will clean itself up in a fairly rapid period of time. All right. We've reached the end of our episode. Alex, tell us what you're working on. Oh, I guess we know what you're working on, but tell us what else you're working on and where people can find out more.
Oh, what else? I don't know what else.
What
Exomoon's
have
all
you
the time.
written lately?
I've got a paper that I'm trying to get submitted in the next few days, actually. A new Exomoon theory paper. I'm quite excited about this idea. Maybe I've teased it before, but I won't say too much until the paper is properly out. But it's kind of a different approach for me. And
Come on, you can tell us.
Cool.
Come
No. It's the internet, man.
All right. Well, if people want to find out more, where should they go?
Follow me on Twitter is the best place. My Twitter handle is just my name, @AlexTici.
Awesome. Carolyn.
You can follow me on Twitter at the Space Writer or at Space Writer, and I'm thespacewriter.com. And aside from trying to get all my new telescope out there when it's not cloudy and snowing, I'm working on a book about planets.
Fantastic. Chris.
You can follow me on Twitter at @TheRealCCar. At this moment, I'm mostly just writing my thesis proposal, so not much sunlight.
Yeah. All right. Well, so of course, I'm Universe Today on all the things. I had 2 really interesting interviews this week on my YouTube channel. One about studying exoplanet atmospheres, and a second on practical interstellar spacecraft proposals. So you may want to come and check that out. Thank you, everyone, for joining us this week. Thanks to all my co-hosts for going over all of these crazy, incredible stories this week. Super fun. Thanks everyone watching us both on YouTube and on Twitch. Thanks to Pamela for engineering behind the scenes, and thanks to Nancy and the rest of the moderation team keeping everything all clean and tidy over in the chat, and for organizing us. We appreciate it, Nancy. We will see all of you next week. Thanks, everyone.
See ya.